Now that we know where some of the most important elements are on the periodic table when it comes to organic chemistry, it's important for us to learn something about how we can use where they show up on the periodic table to make some predictions on our future reactions. There are two periodic trends I want to show you right now. One is what the size of the atoms are, and the second one is electronegativity, how we use the periodic table to understand those two things. And I think after this video, you'll have a good understanding of what those things mean and how we'll be able to use them in the future to understand how a reaction will proceed. Let's jump right in. Now that we know where these elements are on the periodic table, in our last video, we learned about Libet Biknafna, no peas, and fat clowns bring in attention. So we know where some of the most important elements, hydrogen and these, carbon, nitrogen, oxygen, and the halogens, these show up all the time in organic chemistry. I want to teach you two little things here about periodic trends. One, let's focus on the size of an atom. How big is the electron cloud? How big is our atom? So let's just take a look at a few of them and we'll reason through what happens to size. I think it's a mistake to try to memorize. Let's see, left to right across the row is this, and up and down a column is this, because it's too easy to forget that. If you deeply understand why the size of the atom is the way it is, it's easy to remember this periodic trend. So let's start with hydrogen. Hydrogen, number one up here on the top of my periodic table, is one proton with one electron around it. And we may remember from earlier chemistry that that electron is in a spherical orbital called an s orbital, or you might call that the 1s orbital. That's where the one electron is for hydrogen. And when we have helium, we have another proton in the nucleus, and now two electrons in that orbital. If we come down to lithium, this orbital, the 1s, is full. So lithium, because it's the second row down, those electrons go into a second shell, we call it, or a second group of where the electrons can be. And lithium with one extra proton will now have 3 electrons. And beryllium has 4 electrons. But then when we get to boron through neon, this 2s orbital, the spherical one of beryllium, when we get to boron, now that one's full of electrons, so you have a 2p orbital that starts to fill in. And you might remember there's 3 2p orbitals. This is a 2p, this is a 2p, and there's one that's in and out of the piece of paper that's a 2p orbital. That one's kind of hard to draw for me. But as we add protons and we start to work our way across the periodic table, electrons go into these 2p orbitals. And we call these all 2 because they're about the same distance to the second shell away from my nucleus. So you would think that all of these electrons, since we're putting them about the same distance from the nucleus, should all be about the same size. But then as I go down one more column, this is sodium. We don't know that yet, but there you go. Sodium, once we fill all of the second shell up, now I need a third shell. So sodium would be even bigger because I go out to a third shell. So from hydrogen to lithium to sodium, we get bigger and bigger because every time we go down a column, we're adding more and more shells to the outside of the atom. So as we go down, it gets bigger. So between fluorine, chlorine, and bromine, these electrons are in the 2, the second shell. These are in the third shell. These outside electrons are in the fourth shell. So bromine is bigger than, so fluorine, chlorine, bromine, and then iodine's even bigger. So these get much bigger as I go down the column simply because I'm adding shells. I think that one makes sense. The more I go down, the more shells I will add, and the bigger my atom becomes. The other trend as we go across, that was a little harder to understand, but if we refocus on that again, so let's say I have boron. I have 1, 2, 3, 4, it's number 5. There's 5 protons in the nucleus. I've got a first shell, I've got a second shell, and I've got electrons in those. I won't draw the 2s and 2p, but I've got 3 electrons down the outer shell for boron. As I go from boron to carbon, I'm going to put one more electron in that same shell, so I might think it's the same size. But the other thing that changes for carbon is now it has one extra positive proton in the nucleus. Well, what did that do? Since these electrons in the second shell are about the same, all of these kind of going to the same distance away, as I go across, I'm going to add more and more protons as I add these electrons. So I have more positive in the center, pulling on those negative electrons, opposite charges attract, and it starts to pull it in just a little bit as I go across the table. So as I add electrons to the same shell, as I get more and more positives in my nucleus, I start to pull in on those electrons, and it gets smaller and smaller. So the general trend is it gets smaller as I go across a row, and it gets bigger as I go down a column. But it's hard to remember that sometimes, but if you understand the why behind it, it's easy to replicate. Here's why you might care about the size of these. Let's take chlorine and bromine with electrons around it. And I want to make them negative charges. We'll find out later that nature seems to hate charges on atoms. It abhors charges. So since nature hates charges, we find that it's better if you can take that negative charge and spread it out. The more you can spread it out, the happier the atom will be, the ion will be with the charge. So between chlorine, which is this size, spreading out that negative charge over its surface area, how does that compare to the negative charge on bromine? Well, since I'm going down a column, I'm adding another shell. Bromine should be bigger than chlorine, so that negative charge will be spread out over a much larger surface area. Bromine, therefore, is happier than chlorine is with that negative charge. So if you have the option of making a negative chloride or a negative bromide, which one would you prefer to make? Well, I would prefer to make the larger negative bromide. That's one of the things that we'll see in the future in organic chemistry. So the size of the atom, we'll be able to figure out. The bigger it is, sometimes the happier we'll be with the charge. Now let's take a look at another periodic property called electronegativity. Electronegativity, that's a $9 word if I ever heard one. What in the world does electronegativity mean? Well, it's sort of the measurement of how strongly an atom pulls the negative electrons in a bond towards itself. So if I have two atoms and they're fighting over, if I draw a line like this, that means there's two negative electrons in a bond. Let me go ahead and draw E with a minus. How strongly this atom pulls those electrons towards it, and how strongly this atom pulls the electrons towards that, that's the electronegativity. So every time there's a bond, there's a tug of war for those electrons, and these atoms are fighting over it. And the strongest of the atoms, the one that pulls the electrons the most, we say is stronger or more electronegative. Now, electronegativity, the way we measure that is fluorine is the strongest, the most electronegative element that we have. We won't worry about the scale of it, but Linus Pauling came up with this scale, and he gave fluorine the highest value. So fluorine is the most electronegative. So in general, the closer you are to fluorine, the more electronegative you are, the stronger you are at pulling electrons towards you. So how can we use this to our advantage? Well, in the future, you might see something like a carbon double bonded to an oxygen in some kind of reaction. And maybe I have something negative, some other negative molecule that's going to react with this carbon double bonded to an oxygen. Where will it react? The oxygen, the carbon, something else? Well, one thing you can do is if I can see the electronegativity of these two atoms fighting over these negative electrons in this double bond, these four negative electrons, in the tug of war for these electrons between carbon and oxygen, who wins? Which one's more electronegative? Which one is stronger? Well, between carbon and oxygen is closer to fluorine, so oxygen is stronger. So that means for these electrons, if I wanted to draw it another way, the electron cloud is more on the oxygen than it is on the carbon. The oxygen pulled these negative electrons closer to it. So if oxygen has more of the negative electrons closer to it, what charge does it become? More positive or more negative? Of course, if it has more negative electrons towards it, it becomes partially negative. This side up here is negative. That little delta symbol means partially. And this carbon then, if it has less of the negative electrons by it, is partially positive. So this negative thing will attack the oxygen and carbon. Well, since oxygen is already negative and carbon's positive, opposites attract, this negative thing will end up attacking the carbon and not the oxygen. So it will help us predict how reactions will happen in the future. Will it attack this atom or this atom? Maybe I need to figure out which one's more positive and which one's more negative. And then I can let opposites attract. I hope that was helpful. If you could, do me a favor and subscribe to the channel. Give this video a like. That way more people can find these videos so I can help more people on their organic chemistry journey.